Alright, yeah, it should be sort of live-ish, at the moment. Let's see how long it lasts and whatnot. I have to do a little bit of this, whatever, settings thing. Yeah, settings thing. Yeah. Lost all vocabulary. Really is all gone. It's going to get even worse by the time next year I'll be
all vocabulary.
Yeah,
Really is all gone.
I'll be 67 and then I'll really be in trouble. That's supposed to be when everything really goes to hell. But anyway, it's my tough luck. I allowed myself to age improperly and pay the price. Alright, so that's done. And then I have to do this little shitty, stupid thing here. And there, I think I'm done. I can get to the video. So I got a new little pointer. I can move around, a little dickhead pointer. So anyway, that Valerie Rousseau from the Shitterversity, can't even get the subject. It's just so annoying. And so he, I guess to disguise himself, did post a message from my forum on the website, which you're saying, why would he bother doing that? He's not blocked on my channel and he can email me, but instead he had to be secret email. Yeah, he's still doing the loser thing, so he did like a fake email address with .loser, just giving himself away. With this pathetic challenge of explaining a Newton's cradle, and you're just saying, what is this? I'm saying, what the fuck does this have to do with the subject, right? Because the theory about how energy is transferred in a Newton's cradle isn't going to have anything to do with scalars and vectors. It's just not. Okay. So that was kind of funny. And then some other asshole did the same thing. And I just, I don't think he would do it twice, but it's just so bizarre that people think this is somehow a real challenge. So because he said it like it's a huge challenge to explain, when physics doesn't explain it. Now, the Action Lab guy did do a video. I did a response video to it. Frankly, sort of getting to the subject about how exactly the Newton's cradle knows that 2 go in and 2 are supposed to come out. 3 go in, 3 come out, and why that is. And again, well, one of the obvious things you can detect is, well, if I change the mass of any of these little balls, it won't work. Yeah, so that's a giveaway, okay? If I put springs between them, that might fuck it up too. So if I put springs between all the little balls, maybe it ain't going to be 2 and 2 either. So there has to, there's obviously some sort of rules for the simplicity of the behavior, which is the same energy goes in has to come out somehow. Now they don't think the same energy goes in and comes out when you do change the masses. So when you change the masses, then you can have 100 momentums go in and you can have 150 or 200 pop out the other side. So that's their theory, for which they don't have any clinically done experimental evidence demonstrating any of that crap does happen. Credible experiments, frankly. You gotta always use the word credible experimental. Because they don't bother with being obedient to those kind of rules. That things should be credible. All right, so I'll give you what I understand, how I understand the mechanism is working, and my plausible explanation. But I don't think it's any better or worse than some kind of crackpot nonsense they could come up with. But I haven't heard their crackpot nonsense. Even the Action Lab guy didn't really say anything about how the energy is actually transmitted. Beyond the stuff that we know. Alright, so I have done videos on this, so that's the other part of this. It's kind of ironic, is I've already explained this, so it's not some sort of challenge. Alright, so you could just consider this one object. So when they're all the same mass and they're touching each other, in a sense they behave as one unit, in the sense they just transmit right through them. So that's sort of a giveaway also. So, but what you understand, what is been found out, that I could even take a long piece of steel and I can tap it on one end and it will extend on the other end. So you hit it with a hammer on one end, and even if it's really tightly nailed down, the fact is it will expand on the other end. It will, push out. And the idea is you're going to understand that if it pushes out and it doesn't stay pushed out, that means it's going to push back in again, and that the energy will just in some sense travel and reflect and end up back where it started and push the object that hit it back. Now, this would be an interesting experiment in the sense that they could take a very long piece of steel and see if they can change the amount of time it takes for something to reflect off of it. So if I had a big long steel piece of rebar and and I was doing it has to be timed pretty well because the speed of sound, and so it's all about the speed of sound, is the speed at which the pressure, if you want to call it that, the electron pressure moves through the steel. It moves through it at the speed of sound inside that material. And the speed of sound inside of the steel is like 2,000 miles an hour or something like that. It's pretty high. So it's pretty fast. So that's why you need a pretty long piece of steel if you're going to do any of these kind of tests. So the idea would be is you would just basically, do your Newton's cradle thing or a hammer thing or whatever, give it a blow, and see how long it takes for the object to bounce back off. And I'll tell you something. Now, that's something. But the full nature of the reflection, you're still saying, well, what's it really about? And what you already know what it's about is, their wrong diagram of how atoms are constructed, frankly. And the simple argument is that when you're hitting or encountering something, the fact is what you're really encountering are the electrons. Okay, so we can just sort of ignore nucleuses for the sake of this argument and just deal with the fact that I would argue that electrons are always in positions based on where the other electrons are, and that pressure always has to basically equalize. That is, it's like you can't have more pressure between these two electrons than you have between these two electrons. They all kind of have to find a balance because everything is sort of built symmetrically or geometrically. And it wants to tend towards, let's just say, symmetry. Absence of symmetry would create distortions, where if, say, I got rid of this electron, well, then the shape of that atom would go something like this instead. It would change the position of objects. And again, the balance would be recreated between the electrons. So you could argue that the electrons are all hard objects. So this would be my physics statement. All hard objects, hard elastic, are hard elastic because they're just revealing that electrons or atoms are elastic. So the nature of atoms is to be elastic. Now, if you're just hitting one atom, obviously it's not going to be able to be elastic because it can move too freely. So it's sort of like if I suspend a tennis ball in space and I poke it, it's not going to be very elastic just because it's free to move. So it's not going to push back much. It's just going to go. But atoms inside of hard materials obviously are sharing electrons, and so they're very tightly tied to each other. So they're not going to move the whole atom. You're just going to create pressure inside of atoms and the connected atoms, and that's what the speed of sound is inside the steel, is the fact that you're basically transmitting the message, the impulse, from electron to electron to electron to electron. That takes some time, okay, because it has to basically go through every electron in the material. It's going to feel the pressure eventually. So if you took like 10 pounds here, you could argue on this first electron, that pressure has to be pushed through all these other electrons. So here it's going to be 9, and it'll be 8, and it'll be 7. It's going to diminish with distance. But it's just going to take time, for that to be absorbed by all of the material and actually push electrons out of the substance. So like a non-compressible liquid, the steel is kind of like that, except it has this elastic cushion, but it's, a limited elastic cushion. And so basically, if you push on this side, you're going to end up pushing on this side. But it's going to have to be, that push is going to have to move through all of those connected atoms. And the simple argument is yeah, you hit this side, it bounces to this side moves out, and the electrons don't have anywhere to go, right? So you push the electrons a little bit away on the outside. They were this distance, from the nucleus, and then you push them out here instead, this longer distance. And, the thing that's going to happen is they're going to rebalance. If they can't keep going, they're going to get pulled back, essentially, by the nucleus. You didn't give them enough energy to leave, to escape the magnetic force, the charge force. If they can't escape the charge force, then they're going to be coming back, and they come back with the same energy that pushed them out, technically. And so they essentially just re-hit the surface with the same hammer, okay, and you just end up shooting something, reflecting it off the steel, and you get a substantial amount of whatever you put in. You get a substantial amount of it back out again. So that's the principle, mechanical circumstance. So it's basically the elasticity of the electrons, and the idea is if you want these electrons to move at the same speed, okay, with the same pressure, the same motion. So the same motion you pushed in on this surface, if you want the same amount of motion to happen on the other side, you could sort of understand that I can't have more atoms in here. So if I hit, I have a bunch of atoms with a pressure, I combine that pressure into another surface. If this pressure doesn't release the same pressure into these electrons, if there's more electrons, you can understand that the pressure is going to be less. There's not going to, so if I put 10 in, these electrons all have, say, a 10 of pressure. And now I'm connecting them to this object, but it has twice as many electrons. Well, you can sort of understand that I can't increase the pressure to 10, I can only increase it to 5. And so it's not going to be the same amount of pressure that's going to be transmitted because of the fact that there's more molecular atoms to transmit into. So the idea is in a Newton's cradle, all you're really saying is you have a certain amount of MV, okay, pressure, force, weight. You're going to hit the surface with that weight, and the simple idea is it'll go through anything with the same mass, it will travel through unaffected, so not reduced. And then as soon as it gets to the end, okay, it's going to be sitting there saying, okay, these electrons can go. And the fact is, they can go because the pressure has moved right through them all. They all now have the force, and the electrons are going to push out, and the rest of the atoms are going to follow because they all have the same pressure. So all of them are going to go and move because they can. They're free to go. So they will go because they're not tied to all these other atoms. They're independent balls. So they're free to just leave. And so they will with the electron pressure that pushed them in that direction. And so it just flows from, you have the MV here as a vector. It goes through the connected balls, okay, as electron pressure, and then it just leaves again by whatever mass is able to, hasn't diluted it. But if I put a bigger ball in here, then I'm going to break it, because now there's a higher density of electron pressure, and so the pressure on this ball is going to be reduced because it got diluted. So it got, it's sort of the currency argument. This is $5 bills, and to move this one you need $10 bills, and so there has to be a kind of a conversion that takes place where you move the energy through. And the real point is what this is really doing is converting it down. It's taking $10 bills and turning it into $5 bills. because that's the only pressure it can build up is $5 worth of pressure. So this ball won't leave with 10. It'll only leave with the 5. And so you won't have nearly enough momentum to move 2 balls here. You'll only be able to move 1 at 5. That kind of thing. And you'll get a much larger reflection from the other side from all the energy that wasn't used. Alright, so that's a general explanation. Again, I haven't seen their explanation, so the weird thing is right there. I wonder if he's going to link to some explanation. Is he going to provide us the kinetic energy version of this? Because frankly, it doesn't matter, right? When you're not changing the masses, you can make up fake kinetic energy numbers. Say this is 100 momentums. Well, it's automatically because of the squared velocity. Let's say it was the velocity was 10. You're going to square the velocity. That'd be 100. I end up with a number that's 1,000. Okay, for the joules. So you're just making up a number. So it has 100 momentum, but 1,000 joules by kinetic energy standards. And obviously, it's going to be the same thing on the other side because it's the same mass. You haven't changed the mass. So if you don't change the mass, you can make up any kinetic energy number you want to. It doesn't matter. Doesn't matter that you're saying it has this v squared energy, because you're going to get the same momentum that you put in. It's going to be the same momentum coming out in the same proportions. That is the same amount of mass and the same amount of velocity. So the component that's squared isn't going to change. But if you change the mass, the momentum being conserved means, well, now you're in trouble, because you're going to go from having a big M and a small v to a small m and a big V. Obviously, when you square the big V, you're going to end up with a hugely different amount of what you're claiming is energy. And it's just a claim, as pointed out. There's no evidence it takes 25 times the fuel, all right, to spin something 5 times as fast. It doesn't work. It doesn't happen. And yet I have to spend 5 years or more arguing these arguments to what are supposed to be reasonable humans on Earth. I mean, one of the most educated societies, most educated language probably. Well, probably not anymore, right? There's probably some European languages where people are more educated, Japan or something. A higher proportion of people are educated because our multiculturalism has turned the numbers into shit. And there's a lot of shitiversities, frankly. So it doesn't even mean anything to be educated anymore because it's all bullshit. Competence isn't something you're required to be after you complete your formal education. Alright, so I don't think that needs any more explanation. So we'll just have to wait, I guess, to see if there's going to be some follow-up video where they're going to explain how, the explanation I provided is completely wrong for some reason, because the holy scalar energy, they're going to explain what the scalar energy is doing, or something, the magical, invisible, internal, scalar, magical power energy thingy. But that's what they're claiming, is that there's some non-obvious, okay? So the momentum's usually obvious, and it's in your face kind of thing. You can see it, the linear motion of the train, and you can, see its momentum, the MV part, but you certainly can't see the squared part, because you'll see that when you hit the train into another car that's got a mass, the two masses will now share the energy, and half the kinetic energy will be missing. Woo! And let's understand when they say that. I mean, I just remake this argument, so I might as well illustrate that quickly, because it is so bogus. It really is bogus. All right, that they make this claim, about how deformed everything got, and they don't even recognize that deformation isn't really a subject. So you take a 5 mass going 10, okay, so it's got a 10 velocity. Just add 5 mass to it and you end up with a 10 mass, okay, going 5 velocity. And now half the kinetic energy is missing. So all the momentum is conserved. And they've done this experiment, and I'm telling you, it's really almost impressive, you know, that you get numbers that are so close to 99%. Okay, I mean, it really is a very conservative experiment. Now, I'd argue that the reason why it's so conservative is this method of just gently dropping it. Just means that the combining energy is coming from gravity. So in a sense, you're adding a little tiny bit of energy in the downward direction to combine the objects. And that's creating its own friction and contact and noise and all that stuff. So all the noise and all the contact sounds are all being created by gravity, not your linear motion. So you're not really disrupting, just like in gravity, you're not really disrupting your linear motion. You're just creating a tiny little bit of extra friction. That's it, a tiny bit of extra friction with the track because you've increased the weight. And when you dropped it, the impulse weight is twice the actual weight. So this weighs something. You know, the 10 mass going 5 has a weight and a friction. And the friction at this moment was twice that standard friction, but it was only for that one tiny moment. And so that's the only energy, that's the only linear drain. So the only thing draining your linear motion was a tiny bit of extra friction in the experiment. So if you have a pretty good, if you're not losing too much energy per unit of distance, and you're measuring the experiment in small units of distance, that is, you know, the whole experiment takes place in this much distance, you know, friction isn't going to be a big issue. But anyway, so back to my point. So you've lost half the kinetic energy, which is a huge, in the sense that, you know, half the energy that the object had. So if this was 5 kilograms, you know, that's a lot. 5 kilograms going 10 velocity is a lot of energy to lose. You know, it's a lot. I mean, half of that. So it's a significant amount. And so anyway, they'll say deformation, heat. So they're saying that this contact somehow wasted a bunch of the linear motion as heat. Somehow a bunch of heat escaped. Now, obviously, they don't collect any of this, so they don't have any evidence that a bunch of heat escaped. And they certainly don't have any evidence that that heat was the linear motion being used. And that there would be you'd have every good reason to believe that was just a consequence of the gravitational impact of combining the two objects using the force of gravity to combine them. And that was the heat component. So it doesn't even work as an argument. And certainly deformation should be a real loser, because, you know, in any collision, when you crash things, okay, you crash cars into each other, and they crush all the pieces, yeah, that isn't a permanent use of the energy. This isn't where it ends. Okay, the crushing of the metal and the bending of it, that didn't use up anything. It just changed the form of the energy. So you went from having energy in big connected atoms all moving together, okay, in a big object, so a big group like a school of fish, and then all you really did was deform the fish, okay, and now release the fish as individual fish. So you had your fish hit other fish, let's just say, and make them go off. And so you still have your original fish. They're a little bit misshapen now, but you still have them all. And all you did was take the motion they had. These fish were all moving, all right? You know, these fish. They were all moving. They stopped moving, okay? They got reshaped through the process of being stopped, and then they're still moving out here as heat. So we already know that from Joule, that all the energy can be convert it into heat. You can take every bit of the energy, the motion energy, and you can convert it into heat. You can take the spinning wheels. So if I throw a car in the joule tank, there's not only the motion of the atoms, but it'll even count the motion of the wheels, because everything's going to stop moving. When it finally sinks to the bottom of the tank, it's not going to have any more energy. And all of the energy will be in the motion of the water. And the motion of the water is proportional to the temperature of the water. And so, it really was a brilliant way to do the detective work of saying how much energy was really in this thing. And it's not, it's not an accident of physics that they named the joule, the unit of energy after joule, and yet they never did another joule tank experiment. It's not a thing. Universities have atom smashers, they have giant magnets, they have, all kinds of radioactive this and, detector for that. Do they have joule tanks? Not that I've ever seen. I mean, I've never seen a video, except some reenactment of Joule's experiments. I've never seen a video where somebody does a joule tank experiment. And you're saying, isn't that as glaring as the fact that they've never done the Eddington experiment? That in all this time, they haven't utilized this great invention for getting an accurate figure for how much energy something produces? Because all you have to do is turn the energy into something's motion and throw the motion into the joule tank, and it'll tell you how much energy you got. I mean, it's it's so glaring, and it's so much better an experiment. Like the old version, before Joule, was the silly de Chardollet experiment, where they just dented the surface of clay, and then compared the dents. So they dropped round things, and just allowed them to barely dent the surface. And obviously, giving that a huge advantage to the thing with twice the velocity, because it's going to be more pointy when it goes into the surface than the thing that doesn't have the higher velocity, because it's mostly going to hit the flat part of the circle. So one thing is doing mostly flat surface into the clay, and the other thing's doing a lot more of pointy surface into the clay. And another huge advance in physics that isn't noted by physics. This was a terrible experiment, the denting of the clay. Joule tanks were a brilliant experiment, and they never used one for that purpose. And the funny thing is yes, Joule did it the wrong way. In the sense that he put a propeller inside the tank, and then he dropped weights in gravity, and that's all he did. He just dropped weights. He didn't tie it to a horse, or tie it even to an electric motor, or tie it to anything. And that was the real lack of insight. And that's the cause why Leibnizian physics, because he thought that gravity's the same no matter how long you're sitting in gravity, you weigh the same. And you don't weigh the same no matter how long you're sitting in gravity. The faster you go across the scale, the less you weigh per inch. And so the fact is, you need time to weigh your weight. And if you're suspended in gravity, something's holding you up, it has to continually, every second, provide the counterforce. It can't do the counterforce once. It has to do it every second. And so obviously, if something's being suspended by a string, you can understand that there's a constant force for the whole time it takes for the weight to drop. So if you've slowed down the drop, you've gotten a lot more gravitational force. You've had to compensate for a lot longer in the gravity, which means you got more gravity. It means more gravity fell on you. So I guess I could do some of that. The fact that you people, common people, common silly people, don't really understand. I've used the analogy of rain, and that really is exactly how it works, frankly. Gravity is like, it might as well be little steel balls, right? Little tiny, perfectly consistent objects. And they're falling, okay? And yes, they're moving at the speed of light, and there's a certain amount of them every second that goes across this. I could draw a line somewhere and say, okay, this is 1 second. All right, and so this is how many go across this line in the 1 second. You could kind of just argue, that there's a number, and that's our 9.8 number. Okay, that's what you're gonna that's the possible collection rate depending on your size. So if you're a single atom, you just get 9.8, let's just say. But if you're made out of many atoms, you're going to collect many units of the 9.8 because you have all these atoms to collect it. So they're all going to collect 9.8, in terms of how many times they got hit. They're all going to get hit the same number of times. So one atom gets hit the same number of times as 500 atoms. So the feather and the hammer will collect exactly the same amount of this force, okay, that's available going through the object. And it's yeah, you can't, every electron is the same, so all the electrons are going to get hit, and all the protons are going to get hit, and a certain amount is going to hit them, and that's just what they're going to collect. So you're collecting it like a nuclear force. You're collecting it in your subatomic pieces, or what's collecting it, and they're like sails. And it's just saying, how big is the sail? Well, the sails are all the same size, so it's just about the number of sails you have will say how much motion you can collect. But if the sails weigh something, then you can sort of understand, if every sail came with a length of boat, you can't add sails without adding mass. So the fact is that since you can't add sails without adding mass, you can understand that as your number of sails go up, your mass goes up. And what you're really just saying is, I'm going to collect more boat worths. So it's almost, you could just think of each atom or each electron as a little sailboat, and it's just boats worth. They're all connected to each other, and it's a boat worth, boat worth. So one boat worth is the same as 10 boat worths in terms of velocity. But when the object hits something, when you go to collect it, obviously the hammer collected a huge amount of energy, momentum, and the feather collected very little because there's very few boats that are going to hit the shore. So you have 1,000 boats hitting versus 2 boats hitting. Obviously the impact is going to be much greater for the boat that collected more. And so this is all just time dependency. You can't get out of the idea that if I'm in that stream longer, I'm going to collect more and more wind. And I'm going to be, and it's just a fact. And if I'm not moving with the wind, the thing stopping me from moving has to endure the wind pressure more. It has to counter more wind pressure. So if this, again, if I tied a string to it to fight the wind, and I'm holding the string here and the wind's going this way, you can understand that if I'm not letting the wind push it, then I have to be collecting, resisting all of that force. And so if it's, 1 second versus 10 seconds, you can understand 10 seconds doing that is more work than 1 second. I'm going to have to provide an awful lot more resisting force in 10 seconds than I am in 1 second. Adequately done. And such. Only 3 viewers, not too good. And such. So I guess I'll play a video. There's so few. I mean, if people do find it, there's no videos really on the subject where anybody does anything but the standard textbook bullshit. And so they really just don't deal with this really interesting subject, okay, of the scale argument, okay, that you could weigh something in gravity, okay, and it'll be applying a pressure, and it'll read a number on the scale. And the simple argument is you could just turn that scale sideways, and you could do the same experiment. You could say, what velocity do I have to give an object for the same object? Let's just say this is mass, and this is a mass. So this mass weighs this on the scale. What velocity do I have to give the object for it to weigh its gravitational weight? So and there's a velocity. And the fact that physics hasn't done this, right? This is such a simple experiment, so simple. So we've got two physicists here, just insulting me. Why can't they explain why in all these years physics has never done this simple experiment? Just turn the scale and then give something an impulse velocity. Yeah, it's not going to be a constant reading on the scale. It's just going to be an impulse. So it's going to push into the spring, and it's going to read a weight, okay, for a millisecond, and then it's going to release. But we can lock the weight. We can, it's constantly done with a ballistic pendulum. You just let a thing swing, and it's, how far out it went. So it's easy to do, and there's an absolute velocity that this works. I'm arguing that it's actually the same as a 1 centimeter drop. So if you take a mass and you drop it from 1 centimeter, you will double its weight. So 1 centimeter equals 2x the weight. So you can double something's weight by just dropping it 1 centimeter. And that reveals that 1 centimeter is the weight. Because when you're doing it sideways, you don't have gravity pushing it. So you don't have that constant force, and then you're adding an extra force. You don't have the constant force of its weight, and you don't have the extra, because this is just an impulse. The velocity is an impulse energy. You use that up when you hit the scale. The impulse part gets used up. The constant part isn't used up. And so the simple truth is you're not going to weigh twice your weight at the same distance. You're just going to use 1 unit of the weight. So the simple truth is it comes out to 0.44 meters per second. And 0.44 meters per second comes out to be just about 1 mile per hour, which is a nice convenience. So it's just very interesting that you can move anything at 1 mile an hour. And if you measure it on a weighing scale, it will weigh its weight. So move an elephant 1 mile an hour into the scale, and it will weigh 2,000 whatever pounds. Move a mouse, and it'll weigh whatever, 17 ounces. Yeah, I don't know, something like that. This is so simple. And so it'd be just nice, if these people who are all doing all this ragging, all this bitching, all this complaining, this would be really interesting for them to just give me their take. Why did it didn't occur to physics to do this simple thing? Just take the scale and turn it and measure. Because frankly, what it proves is that when you're sitting on the scale, weighing your weight, it's exactly the same momentum. Your MV, if you could see your MV, the fact is it would be the same as this MV. This 1 mile an hour motion is essentially the same pressure you're applying to the scale. So the MVs are essentially the same. So when you're sitting in your chair, you're actually moving 1 mile an hour, but such a tiny amount of movement that you can't see it. Because the ground keeps pushing you back. But that little push in is 1 mile an hour. And then you're pushed back. 1 mile an hour, push back. 1 mile an hour. That's your actual momentum. That's what it comes out to because gravity's pushing you in, and the earth pushes you back up, and the earth pushes you in, pushes you back up. This is you're going down only 1/2 the time, you could argue, right? So you could sort of understand that, only half the time I'm going the right direction. So right there you could say, well, whatever the force is, it's half of what it should be. So you could say, okay, it's really 2 miles an hour because you're only doing it half the time. Some kind of crap like that. But whatever half the time means. And so if I make this frequency very, very high, you can understand that's an awful lot of offs. And so, it just depends on how you understand the forces moving the speed of light. So who knows what the oscillating frequency is, what the math would be to derive, okay, how 9.8 meters per second of velocity converts into 1 mile an hour. But that's what it converts into when you actually crash into a surface. The surface that has the gravity, frankly. You could obviously duplicate these experiments with magnetism too. So you could create an artificial gravity, by just creating a magnetic field, and it would be essentially the same thing because it's going to substantially obey the same kind of rules. Now, the fact is, magnets are kind of like, instead of r squared, it's kind of an r cubed rule. So, but you would know that the surface would certainly have the same rule. So if you had some force detector or something right on the surface that wasn't disturbed by the magnetic field, you could understand that you could do the same type of experiment in terms of figuring out how heavy a magnet. Well, that really won't. Because how heavy a piece of steel would be attracted to the magnet. With what pressure, and then again there would be a certain amount of electricity you had to put in to create a certain amount of pressure. I haven't seen any experiments where they do that, where they crank up the electricity on the electromagnet and then detect the pressure that the steel is creating with the surface of the magnet. Nothing. It's just kind of glaring that none of their physics is doing any of this crap the dickhead is insisting I do, which is explain things and figure out how the thing is mechanically works. And it's clear in all these hundreds of years, none of these physicists have thought that this would be an interesting experiment and this would be something worth knowing. It's never been suggested that, hey, somebody should do these experiments clinically, figure out these numbers. Nothing. The very fact that in all these years, all this time, even with the Newton's cradle, they make all these claims and they haven't done any of these experiments. Where you would, Newton tried, but obviously Newton had limited capacity to measure time, to do any of these experiments, to really know a velocity. He had to do it. He couldn't record anything on videotape. He had to see it happen in front of his eyes. And all this stuff happens kind of quickly, blah, blah, blah. That's why Galileo, got smart and made everything on ramps to slow everything down so he could see what happens. But some things you can't slow down. And you certainly can't slow down, a Newton's cradle except by making it bigger and bigger. So Newton did do that. 12 foot, but, he can only do so much with getting masses right. But nobody really did this simple experiment. Just take it and just keep making the mass, start with a 1 to 1 and then go 1 to 1.1, 1.2, 1.3. Just incrementally, change the mass and the mass coming in and just measure the two values. How much do you get this way and how much do you get that way? They don't have that as a clinical experiment anywhere. It just doesn't exist. And this is the kind of thing you can do in a vacuum chamber to make it even better. They haven't done any of it. The fact that universally the people opposed to what I'm doing here universally hate the idea that I'm arguing for these experiments. They won't join in and say, it'd be really great. It's disappointing that physicists didn't think it was useful, because it'd be really nice to have this evidence. Again, they've never crashed the cars. The Mythbusters had to do it in one of their cartoon shows. It's a cartoon show. It's not serious science. It's all a big joke. And but at least they did the experiment that physics never did. you know, and they could make a nice consistently crushable car, that is without a steel frame, and just make it out of a very crushable material that crushes rather consistently like a spring, and demonstrate that there's really 4 times the energy inside of the twice as fast car. Now, when they did, obviously the answer was no, there's only 2 units of energy in the car, that's all. Car crushed twice as much, 100 miles an hour, twice as much as 50 miles an hour. But shouldn't we have 10, 20, 30, 40, 50, 60? Shouldn't we have all of these experiments to know exactly how proportional it is? And I'm the only person that can suggest that. I'm the only person who thinks that would be a great idea, and it wouldn't even be that expensive, right? I mean, compared to other scientific budgets for even one satellite costs more. They could do this for a very small amount of money, and none of this is done. And these are all people defending science, and they're not suggesting any of these experiments need to be done. It really is amazing. The hostility. Yeah, it is amazing. So 3 still. Well, that's just not acceptable. 3. Can't do much with 3 viewers. Unfortunately, I found out you can't, I thought I could just pause the video, but you can't. If you're paused for more like 60 seconds, YouTube just ends it, the stream, so that doesn't work anymore, unfortunately. So yeah, it's only a very brief pause can I take. Apparently. I could always try it again, but I think, the last time I tried that, it didn't work. 2-minute pause was too much. Alright, so I guess I can play a video. I mean, it's, it's just disappointing that the audience is so limited. People's choice, and this is the world the people are choosing. They're choosing to be dupes and fools and watch, brain rotting crap instead of paying attention to anything important. And that's sort of the nature of idiocracy. So, nothing I can do about it, frankly. And so I'll just do my part. Make reasonable arguments to a bunch of deaf and dumb morons and such. Alright, so this is a video by something called Step by Step Science. Now, seems a likable enough guy, but he doesn't have a great voice for radio. Maybe he's really attractive, but he talks kind of fast and slowly. What I mean by probably, and you're just like, what did you say? It's a little bit too. He doesn't speak that perfectly pronounced English language kind of stuff, so it is a little hard to grok his statements sometimes, which it's just irritating. I'm just pointing it out. It's there and it's irritating, so I point it out. That's sort of what I do. I notice things that irritate me. Alright, so obviously I'm saying that all this crap basically is the same thing. Your mass, okay, obviously your mass determines how you collect force in the universe, and so it will be your weight is what gravity on the surface of the earth creates, and so we can use that as a unit. The energy, the work, the power, the pressure, the heat, what did I leave out? That's all the same stuff. You can't, that's the joule argument. It's all the same thing, okay? See how else to say that. That's weird. On the white surface, his little dickhead falls off. Anyway, So, yeah, what was it? So, yeah, so they're all the same concept basically, and it's just mass with velocity is your energy. So anything moving has a weight, applies a pressure, and can make heat, can make other little atoms move. But it always has to be atom for atom, electron for electron. It always has to add up to the same mass moving. So the same, the the mass of the electrons and protons, for example, times their velocity here has to equal what you end up with here in the universe. You can't change those numbers, basically.
I'm going to go through an overview
Wait, can't hear that at all. Ah, because the volume wasn't on.
of 5 very important topics. That would be mass, weight, energy, work, and power. Before we get started, please don't forget to subscribe to my channel, Step by Step Science. Get all my excellent physics, chemistry, and math videos. When I look at my YouTube, and as I see that so many people who watch my videos have not subscribed. Please subscribe.
So this is what you have to tell your audience. You know, so I'm just saying, you're going to do a physics video and you have to explain how the internet works to the people. You know, that you need to support things or they don't be supported. Yeah, if you don't support them, it won't be supported. Oh, I didn't realize. Oh, so pathetic.
Support my channel, click the notifications bell, give us a thumbs up, leave us a nice positive comment, and don't forget to share this video. In addition to that, I made a bunch of other teaching and learning materials, which you can find on my Teachers Pay Teachers website. It's all there, whether you're looking for example problems, practice problems with all the solutions.
Right, so it's all the same crap that's in 4 million other places doing the same textbook bullshit that really has nothing to do with a concept anywhere. So no concepts, just silly equations that often are so useless, like MGH. It only works in some bizarre circumstance where you can place a mass in a location and drop it. It doesn't work anywhere real.
For a bunch of different topics, puzzles, fun things to do, activities to do with PGT at interactive simulations. It's all there at my Teachers Pay Teachers website, and the link is in the description below. Now, I have also made detailed videos about each of these topics, which you can link to some of those in the upper right-hand corner, and I'll also put links to each of them in the description. But in this video, we're going to do a quick...
So whatever that means. So if he's made these videos, they're not really... I mean, they all have more than one video doing something, but it's all the same stuff. So you can just see... Well, if you could see, they're all in the recommended videos, and it's all the same crap we've heard 4 million times.
Overview for mass, weight, energy, work, and power. And of course, we're going to start off with the very basic thing, which is mass. What?
So one of the basic parts of mass, I'd argue that physics is just wrong about. So, and they really, I have never heard any reasonable explanation for why I'm expected to believe that a photon has no mass. I mean, why would I think it has no mass? It conveys momentum, right? So I think everybody agrees that photons... Oh, yeah, well, I have to move that, don't I? I can't draw with the video on top of the screen. It's always something. So many details. So, I mean, I'm obviously arguing like the atom is... magnetic. Okay, so obviously I'm arguing the electrons are in standard positions. They are not swirling around at 4 million miles an hour, 400,000 meters per second, or some wacky amount of... They're not orbiting. They're magnets. They're stuck in locations like magnets would be. Alright, so they're applying a force at each other, just like magnets, a repulsion force between the electrons and an attracting force to the proton. Okay, but it's not really attraction, obviously. It's just the absence of a push. But anyway, and so that's the mass of the atoms is just the mass of the electrons and protons, but that's all there are. The neutrons are just an electron and a proton, so you just count every neutron as just an electron and a proton. And then you have you know, a photon, and it's going to interact with atoms. So, you see, I mean, the whole thing is so messed up because they don't even, physics doesn't even explain to people that, photons are really big. The wavelength of the photon is 500 atoms, okay? It's very, very big. And so if you understand that the photon is also polarized, well, the polarization would be 500 also, close to it. So you got this huge thing that interacts with a surface, something that's 500 atoms across. Obviously, it can't be one electron it's interacting with. So it's obviously interacting with the surface, and the very fact that it creates electricity is sort of a giveaway that obviously it has to be causing atoms to create the same kind of electron mobility that electricity represents. That is, you have to have caused an electron to gain enough momentum to be cascading from atom to atom. So it can't really be logically understood that it's one electron makes a photon. But anyway, so obviously I'm arguing first for a much more rational magnetic, let's just call it atom, rather than swirly gravity kind of atom. And there's no orbiting crap. There's energy levels. That's a very good word. Energy level, meaning closeness to a proton. So the closer they are to the nucleus, obviously the stronger the attraction force. So the repulsion force, the force locking these things in place, has to be stronger. But obviously it would be, because it would be closer to the nucleus. So the electrons would be closer to each other, meaning they would be applying more force to each other. So it all makes sense, frankly. So that was a big mistake of physics. This silly, orbiting bullshit that they, that they make an atom into. That ain't what's happening. Anyway, when they share an electron, they literally share it. It's sitting right here, and they share it. Both atoms are using it in that position. It doesn't disappear and go somewhere else. It's being shared in that location. So anyway, I'm arguing a photon is just pieces of energy, so like quanta, as Einstein would say, and that the wavelength is just the distance between, the quanta. And the polarization just means that, they fly parallel to each other, but they don't fly in line. So when you shoot electricity up an antenna, the pieces aren't right behind each other. They're separated by, the speed of the electricity in the thing. And so that's what you're ending up with as your polarization. So they're all flying parallel, but not in line. And so that would be a photon. So a photon would look something like these three dots. They hit the surface, and they push on one electron. That electron pushes on a few atoms. Then another piece hits and pushes on an electron. That gives the electrons even more pressure. And then that third piece hits and gives them even more pressure, enough pressure to keep them moving. So it's just a tipping point argument, that you're applying the pressure in such a manner that you're adding motion to the electron. So the electron is moved, and then it's pushed again, moved, pushed again, moved. It's not the same electron, but you're pushing on the electron pressure and increasing the electron pressure in this linear motion. And you end up with an electron finally going fast enough that it can keep going. It gains escape velocity speed, and it stays escaped. It's the simplest argument. All right. So in that diagram, the argument would be that obviously this is kind of a Sisyphus argument. Sisyphus has a mass, Sisyphus weighs something. And so he's got a jetpack that always makes him go the speed of light when he's free. But if he's pushing a boulder, like an electron, well, obviously now he can't go as fast. The jetpack is pushing a lot more atoms. A lot more mass. So he goes proportionally slower based on his mass. But these little dots they have a mass, So a photon, if you count the three dots of the photon, it's a real Planck unit of mass. This is a Planck unit of mass. It's going to hit the surface at the speed of light, of velocity, and it's going to represent a momentum. Now, it's a tiny amount of momentum. It's 10 to the minus 30 or some kind of silly number of joules, but it's a real amount of impact momentum. And I don't know why physics ruined that. So it's the same MV works in this whole system. The photons have MV, the electrons and protons have MV, the atoms collectively have MV. It's all, the planet has an MV. They're all just collected units of vectors. These are all just little vectors. And all you're saying is that the Sisyphus is a vector. He can push boulders with a vector. That can push atoms with a vector. So it's all vectors of momentum. Probably satisfactory. And such. Oh, there's a couple of commenters. Let's see. Sorry that you've had to endure a lot of hostility all this time. Yes, my whole life. It's really been unpleasant. I've never been in non-conflict with the shitty world. Is that an actual head or strawberry ice cream? No, it's actually a... it's actually... Okay, hopefully it's... No, it really isn't. I can science that said he is working on another video. So, yeah, I don't know. Like I said, completely erroneous, like not connected to any subject I've ever discussed. It's just always going to talk about the tissues inside of a tree. Phloem and xylem. What's the subject going to be? That's just so funny. Because obviously it's so obvious the subjects I've been interested in. And it's like, where did he get this idea that somehow I have a unique theory of how energy is transferred through steel balls? Yeah, I don't have a unique theory for that. I think I might have the better theory, but I'm just saying it's not going to be a theory that you can find the scalar part and the momentum part and separate them somehow, because they won't be separable. Alright, so I'm archiving your channel right now, Gary. Don't worry, you won't lose anything. Yeah, well, whatever. I'm sure, hopefully people do that stuff, because who knows what Google's going to do someday. Who knows what, just can't know anything. You really just can't be certain of anything. Nothing's trustworthy. And that's, it's a weird new world we live in. But whatever. I can only do my part as stated. I probably should have archived more of my videos, but frankly, I see them as, they get better and more concise with time, so I could say, well, I could throw out all the ones that are more than 10 years old and just get to the better points now, because I know where I knew something was wrong 10 years ago, and I couldn't isolate it as well as I can isolate it now. So, I certainly knew that entanglement wasn't happening in the double slit experiment, but I couldn't perfectly articulate why that explanation is so silly, because I couldn't explain why there was a double maxima and why the fringes change size and why and now I can explain all that. But it's funny to tell people, I have 5-minute videos on the subject, and then there's a little bit better 10-minute videos on a specific subject. Respond to those videos. And instead, they find some other crap to talk about. Oh, the Internet Archive isn't very dependable, frankly, as time has demonstrated. I mean, it's captured a tiny portion of the old Internet, and that's sort of sad. But whatever. It's just expensive still to... hard drives are not terribly reliable, and you can't trust anything, so you have to make redundant copies, and I just don't spend money, so I'm not gonna I'm just too cheap. But it is getting a lot, I mean, you can get a terabyte of disk space fairly cheap, so I really don't have an excuse for not archiving myself, but yuck. I don't want to do it. So I know other people have, so I just know that it exists. I have some of them that somebody sent me on CDs, so DVDs. So I have some of the older videos. I wish I had some of the original before YouTube broke them and reduced the resolution, because there was a few videos that really got killed. I mean, there was my 1000th video on the Inventive channel was kind of, I did some work on it. It was kind of a funny video. The wild horses or whatever that, so what do you, Hannibal Lecter video. The resolution just ended up getting ruined over time. But anyway, enough of that. So it's not really a viable subject. So let's get back to this crap and such.
Is mass. Well, mass, there's maybe 2 or 3 different definitions that you could use. Maybe the most academic one is a measure of an object's resistance to...
Okay, so resistance to motion is, again, just... Why would they say that? Because it's not resisting motion. The argument was that, this was a substance, this motion thing. Quantity of motion. So obviously most of the physicists at Newton's time obviously thought of the motion as something possessed. That it was like, if you want to think of it, a ghost, but I'm just saying it was like something possesses the object with this quantity, and the quantity can fall out of the object. It can be taken from the object and moved to a different object, and then moved to a different object. And so this whole idea of it, there's a resistance to motion. There's no resistance to motion. Now clearly friction creates a problem, static friction. Because if something's sitting on a surface, it's going to start gluing itself to the surface. To move it, there's going to be some resistance, but you have to overcome the force of gravity creating friction. But if there's no friction, there's no resistance to motion. The object just says, you have to give me the motion. I can't move until you give me motion. And you have to give me enough motion that all of my electrons and protons can move. So if you give me too feeble an amount of motion, well, I just give it back to you because I can't use it. I need enough to make everything move. And that's about the only standard there is. But it's just wrong to say things resist moving.
Change in motion. The more mass you have, the harder it is to change your motion. Now, sometimes...
So, yes, that's true. The more it needs, okay, but you have more pieces to push. So, yes, it's not a surprise that, a little red wagon, really easy to push. Cadillac Eldorado, not so easy to push.
People like to say the amount of stuff something is made of. I like to use this definition in my class. It's the amount of matter than an object.
Right, so then you've broken the connection to the force carrier force. So the force itself obviously is carrying this idea of momentum, mass and velocity. It's doing an exchange, it is being collected by an object and giving it a proportional increase in its mass. So if I hit it with 2 photons, I get twice. Hit it 3 times, 4 times, 5. I can increase something's motion by hitting it with more and more of that raw force. So that definition just ruins any idea, any hope that somebody might occur to them to say, well, if it has momentum, if a photon has momentum, then it must have mass. You can't have no mass and have momentum. It's kind of ridiculous.
Contains. All right, so the more massive you are, the more matter you have. And what is all that matter made of? The building blocks of matter, of course, atoms, and that includes protons, neutrons, and electrons.
So it really just contains protons and electrons because they already know this stuff. Neutrons decay into an electron and a proton and an antineutrino. So you can forget the antineutrino and just recognize that no, a neutron is the smallest dipole. It's just an electron and proton smashed really close to each other. So from a distance, it's always going to look purple, but it's not purple. It's blue and red. Okay, it's got the plus and the minus. It just looks neutral from a distance. But when you get close up, you're going to notice, oh, it's red and blue.
Okay, so the more massive, the more protons, the more atoms, and the neutrons and electrons you have. When we
Right, now if they
mass,
had those masses correctly measured, you would argue that your weight, okay, should match your mass. Okay, so the two things should be the same thing. Your atomic weight should be your weight.
we have an equation symbol. When you put mass into an equation, you use the equation symbol as M.
Exciting.
Then we use the unit is the kilogram. Some people think, well, the base unit for mass is the gram. Well, in science, chemistry, physics, the base unit for mass is the kilogram.
So this is another one of those videos where you say, I wonder what audience he meant this for. Because it's... I don't know, it should just be the, 4 and under, and then, 10 and above. This is definitely not 10 and above, I mean, it really should be something like high school and then college, or maybe these would be decent lines. But I don't even think high school would have a problem with understanding gram and kilogram, especially a modern high school where they're not teaching both, metric and English systems.
And we could write that down something like M equals 65 kilograms or M equals 12.5 grams. A lot of times when we're in school...
So he just makes up silly numbers. He doesn't even connect them to anything we know in the real world. So he's just saying, oh, here's an example of a number that would be a mass. Oh, it's not very exciting. I don't even know why he did this. He should have just said, well, 65 kilograms is, 650 grams or something like that. Would have been more useful.
We don't have kilograms of stuff. We have only grams of stuff. So we do use grams, of course, in other measurements. But when you put them values into the equations, it needs to be in kilograms. All right? And mass does not depend on your location, as your weight does, but your mass does not depend on your location. Wherever you go, you always have the same amount of mass.
So again, that's not even true by their own physics, because Einstein will tell you that you can go somewhere, and if you're moving fast, you're going to weigh more. You're going to have more mass somehow, which is crap, obviously.
All right, and you can see, for example, like here, this alien, this guy's big, and this alien, this guy is small. We can make the assumption that he's bigger, he's more massive, he's smaller, he has less mass. Now, mass, of course, the amount of mass also depends on your density and things like that, but for the two of the similar objects, the bigger you are, the more mass you're going to have.
Yeah, well, see, that's
Imagine if
bigger.
we could tell everyone here that Liberty Mutual
Is
customizes car
almost a
insurance.
really sloppy way to say it.
All right, now,
Because obviously you can have a big, giant, huge ball of styrofoam, and a little tiny ball of titanium, and they can weigh the same, and they won't look they can have the same mass, and obviously it won't have anything to do with size at all. So that's, if you're going to bother teaching the little ones, you ought to teach them correctly, that they shouldn't be confused by size. Size isn't mass. Number of electrons and protons is your mass.
Once we know your mass, then we can calculate your weight.
So calculating is kind of silly because you just measure it, but whatever.
All right? And when we calculate your weight, the weight is the force of attraction between two objects that have mass. So in order to have weight, in order for you to actually weigh something, you have to be on, in this case, on Earth.
All right, so this is just another word where you're just breaking the concept, because all weight is compression on a force-detecting object, an object that can collect force proportionally. So you could sort of understand it that in a way the pressure of a thermometer is a weight. It's getting pushed, and that the spring compressing is a push, and that's all you're measuring is a momentum, and you can have a constant force pushing on you, giving you momentum, or you can just have an impulse energy. You can just have a velocity you acquired, and there's no force giving you more. There's no force backing you up. As soon as you hit something, you transfer all you have, and that's all you have. There's no hand still pushing you.
Because it's the force on an object due to gravity. Okay, it's the force of attraction between two objects. You have weight because you're on Earth, and the Earth is pulling down on you.
So again, there's really no point in calling it something different, right? Turning the scale sideways and reading a compression on a spring, it's all the same thing, and there's just no reason not to recognize that it's all pressure or weight, momentum.
Now, the equation symbol, there's a different way. Sometimes people put a W. I don't think it's so good to put a W. I like to put Fg, which is the force due to gravity, is the equation symbol that we use, such as in Newton's second law, Fg equals mg, as we'll go over in just a moment. And then the unit is the Newton, named after Sir Isaac Newton.
So the unit is meaningless. It's just, I don't even know why they invented it. It's just the weight of 100 grams. So what you just say, why not? You're right back to just putting it back into kilograms again. So why not just say the unit is a kilogram? I mean, why bother with a Newton? It's redundant and not very coherent to anything. There's just no reason to use a Newton.
And we abbreviate that with a capital N. And we could write that down: the force of gravity, the weight of something is 15 newtons, and the weight of something is 0.75 newtons, okay? Your mass is measured in grams or kilograms. Your weight is a force. It's measured in Newton, and it does depend on your location. If you take your mass to the moon, you weigh less. You have the same mass. If you go way up in the air, then you're going to have the same mass, but because you're...
So it's like, let's see, there's 2 pounds to a kilogram, so that would be 20 newtons. So the average person would... A pound would be 20 newtons. So you would, so if you weighed 100 pounds, you would weigh 2,000 newtons. I don't know. Yeah, well, whatever. I never even bothered thinking about it, but I mean, it just, what use is this word?
Farther away from the Earth, then your force of attraction is going to be less. Okay. Now, when we calculate the weight, okay, then we have, for example, the Earth, and you have somebody that's on the Earth, okay, like Zombie Girl. She is attracted to the Earth, because she has mass and the Earth has mass. And that force of gravity pulls straight down.
All right, so obviously her mass is irrelevant. You couldn't feel it, you couldn't see it, you couldn't watch it. It would be totally meaningless in terms of any motion that you would have based on your contribution. So it's really just about the Earth being a gravitational deficit in the field around the Earth. Her capacity to move mass is so completely irrelevant that you can't see it. Okay, it doesn't do anything. So again, just this is a poor way to explain it to kids, I would argue, and these silly graphics don't help.
Towards the center of the Earth. So we kind of use those two terms interchangeably, that your weight is equal to your force of gravity. Now, a lot of people don't actually ask you, oh, what's your force of gravity? They ask you what your weight is. But really, it is your force of gravity between you and the Earth. And when we calculate weight, we use Newton's second law, but we use it in this form. Newton's second law says F equals ma, all right? And that's what we have here. But we like to use, when we're on Earth, Fg equals mg, because we...
All right, so we know this is this standard law that Newton said this, Newton didn't say this. Newton said the force is completely equal essentially to the change in your momentum. So however your momentum changes, that's the net force that acted on you, and it's that force equals the change in your momentum. So if you have no momentum and then you're given momentum, all of the momentum is the force. So you could say force is momentum. You're merely absorbing momentum from something called a force. You now possess whatever the force was. It's now inside of you. The force, okay, just moves inside of the mass and now lives there until the mass hits something else, and now the force goes somewhere else. But that's how it works.
Know that this is the acceleration due to gravity at the surface of the Earth. So this is the...
Right, so we can all say how much we weigh, and it doesn't matter. We're always adding the sentence that says, in Earth's gravity. Yeah. So, there's no point in wasting time with all that crap. But yes, your mass is the same as your weight as long as you're using gravity as the standard. Gravity, Earth gravity.
That you're going to use to calculate weight. Fg is the weight, or the force of gravity, which is measured in newtons. M is the mass, which is...
So the weight or force of gravity measured in newtons. So again, just that doesn't even mean anything, okay, because it's really in kilograms. The newton is 100 grams, so what are we playing around? It's 1/10 of a kilogram.
Measured in kilograms. And then G is the acceleration due to gravity, or the...
So that's the 10 number, almost 10. Okay, that's causing the newton to be 1/10 of the kilogram. So again, just not complicated. And it's just so proportional. It's just the way momentum works in terms of its proportionality. You move 10 times the distance in the gravity, you have 10 times the weight.
A gravitational field strength, and at the surface of the Earth, it's basically always 9.81 meters per second squared. All right, so you want to calculate weight.
So no squared necessary. So I don't think when I was a kid they did this squared seconds thing. So this is a modern thing where they've done this obsessively, where they always put this stupid squared second. It makes no sense. What sense does it make? It's 9.81 meters per second of added velocity. It's not second squared. And it's clearly in 1 second units. It's a ratio of what you get per 1 second. How can it be 9.8 meters per seconds or second squared when it's in 1 second units? It's in 1 second units. I can't believe I have to have this argument with people. It really does surprise me that this is something they will defend when it's so obviously misleading. I mean, it's obviously misleading. I mean, it's in 1 second units. You can be in the gravity 2 seconds, 4 seconds, whatever number. That's how many units of added acceleration you got. How is that second squared? It's just so evil. Alright, let's see if there's anything here. Let's see. Okay, archiving crap. I'd like to hear what physicists think about your Volume 1 spring video. Yeah, exactly. I would like to hear somebody make an argument and explain how, they have a ton of experiments where they call it super elastic and all the energy is conserved. And it's like, well, not if it's using a spring, it's not. So, I mean, it's just so obviously a flawed experiment. I mean, you really, some of these experiments, you're trying to illustrate an explosion with a spring. And it's not a very good illustration, frankly. You need a real explosive because the spring does have this critical flaw. That the faster something moves away from the spring, the faster the spring's moving. And the faster it's going to be moving after the object leaves. Alright, the fact that you can see a spring wobble after it leaves is a sign there's energy stuck. Obviously, that's my point. But yes, thank you for restating it for the readers. People who like to read a video. There, you've said something plain and simple for the readers to understand.
You put in the mass, you multiply it by 9.81, and you get your weight. Okay, so that's mass. And then weight. Now we're going to talk about energy. We're going to talk about mechanical energy, and that's gravitational potential energy.
Right, so there's no potential energy in this context. So this is, again, I've given a simple analogy. You have a boat on the side of the Mississippi River, just sitting on land. It doesn't have any potential energy, okay? The river has a lot of energy. So you put the boat in the river and it moves. Well, that's the same thing as me letting something go in gravity. It doesn't have any potential energy. It's just how much time are you going to allow it to move in the river. And the longer it's in the river, the faster it'll go until it's going the same speed as the river. Simple argument. You're going to cross the river. It's about how long you are in the river will decide how far downstream the river pushes you. If you can swim really fast, you get pushed only a little bit. You swim really slow, you're going to get pushed a lot. And that's exactly how gravity works. And it's just really, it's so imprecise to talk about objects that aren't doing anything energetic and claiming they have potential energy when they don't have anything until you let them go in the gravity.
And kinetic energy. So gravitational potential energy is the next thing, of course. Now, in general, potential energy is stored energy. You can store energy when you stretch.
Right, exactly. So, but all these examples, like a water wheel, and then you drop it into the stream. The water wheel didn't have any potential energy. The stream has the energy. So lots of this stored energy is stored in flywheels, so to speak. So you could argue that are springs, for example. So you could argue that you can store energy in atoms by creating higher pressure between the electrons. And then the electrons can release that pressure, if you break the compound, change the arrangement of the molecules. You can reduce the amount of pressure the electrons are under. So you can store energy as compression, and then you can release the energy as decompressions. So that would be the storage, but this, the storage is all being maintained by that force that is constantly bouncing between the electrons. So it's all active energy in a sense. It's never inactive. It's just that once it's stuck in a circle, I could spin something with a little dot on it. I spin it fast enough, you can't see the dot anymore. So it doesn't look like it's moving anymore, but that's because it's moving so fast. And the same thing is happening in these systems of storage. You're just storing something in a circle, or storing it going back and forth wobbling. But it's stored as active energy. The energy is never dead, never stops. It's just you put it in some place where it's just vibrating in some little location. So you can't see it because it's not doing this and this. It's doing this. Just like you right now in gravity. Your atoms are moving up and your atoms are moving down. You can't see any of it, but it's happening. I mean, it's just so... I just don't understand people can be hostile to this perfectly sensible and reasonable explanation of how this physical universe works. Why are they so hostile?
Rubber band, you store energy in food, you store energy in a battery, okay? But when we talk about gravitational potential energy, this is our definition for gravitational potential energy. It's the energy stored by an object because of its position relative to other objects, okay? So that is how you...
So that doesn't mean much, right? Because it's obviously has to be in relation to some object creating a significant amount of gravity, because you're not going to move, you know, because there's a piece of dust next to you. It just ain't going to happen. So it's just a kind of a silly definition. So we know it's just about how long are you going to be allowed to free fall in the gravity. That'll decide how much energy you can collect. And as soon as you make contact with something else, just like an electrical conductor or a charge, I put a charge on something and then I contact it with some other piece of metal or some other conductor, and it drains all the charge away. So as long as you're not connected to anything, touching anything, you'll free fall, collect the gravity, and store the energy in your motion, and then you can release it when you hit the ground. Duh. You can give it back to something else.
That's the definition that we're going to use for gravitational potential energy. General potential energy is stored, but when we talk about gravitational, we use this definition. Okay, so the equation symbol that most people use when they talk about potential energy is PE.
Yeah, so that's just baby talk. So, you know, I mean, this isn't really high-end physics to talk about the potential energy and the gravitational energy and all this other stuff, because we know it's real, you know, that there's a source and a destination. You know, and again, the Descartesian view is so reasonable in terms of just recognizing this fact that the energy's been somewhere before it got into your object. It was somewhere before then. It was somewhere before then. It's always on the move. And you're just saying, what object is it in right now? Right? I move my hand, and now the atmosphere is moving. The energy is going in all kinds of places. Okay? It's not here anymore. It's certainly not there as motion. It could be there as heat. But it's not there as motion I can see anymore. But it's always somewhere.
All right. You might see sometimes people write GPE for gravitational, or they put a G down here for gravitational, but we're going to use PE.
So we're really talking about stored energy. So this is this potential thing is just a way of breaking that understanding. And again, the fact is that you're going to understand that the storage is in the form of you either put your water wheel in the water, or you don't have it in the water. So when it's not in the water, it can't collect any energy. When it's in the water, it can collect energy because it's making contact. So it's just like, again, an electrical argument. You need a conductor to drain away the electricity. It won't go anywhere until you drain it. Allow it to go somewhere.
And the unit is the joule. Energy is measured in joules. And again, you could write that down, for example, as the potential energy, PE, is equal to 507.
So these numbers are always just preposterous exaggerations. It doesn't have anything to do with anything real. And if you actually measure the momentum, you're going to get some number that'll be much less.
25 joules. Okay? Now, when we calculate gravitational potential energy, this is the equation that we use. PE, the potential energy, is equal to mgh.
All right, so mgh is only by accident accurate in the sense that the height, as Galileo sort of pointed out, you acquire velocity in 1, 3, 5, 7. So the acquired velocity becomes a huge amount of the distance you travel. And so that's the reason why this works for just dropping something in gravity. But the fact is, if you already have a velocity, so if you're a meteor coming down towards Earth, mgh isn't going to be of any help at all. The height won't make any difference. The only thing that's going to matter is your speed. How fast are you going to go through the gravity? If you're going across the stream, you're swimming across the stream, it's not going to matter what the distance is. The only thing that's going to matter is how fast did you get across that, out of that water. The water's the thing moving you, and the faster you get out of the water, the less you're going to have been moved. And that's the truth of it. So this formula does not work. It's not universal, and it doesn't work in, I'd say, 99% of the real world cases. It's of no value, because nothing is placed into locations. Everything has to get to locations with an existing velocity. And if something has an existing velocity, it means they're not going to move through the gravity at the free fall rate. They're going to move through it at some other rate.
PE is obviously the potential energy, which is measured in joules. M is the mass. Now, when you put the number, the mass, into the equation, it must be in kilograms. If it's in grams, you need to convert it first to kilograms. And G, again, is the acceleration due to gravity.
And so again, this is only useful in a specific free fall example where you don't interrupt how fast the thing is falling. You don't take away any of its velocity. As soon as you drain any of its velocity by rubbing it against a brick wall or doing anything like that, mgh is meaningless.
0.81 meters per second squared. And h is the change in the height.
Because the real truth is it's mgt. The formula that works in all circumstances is mgt. It's about time. How long are you in the gravity? How many units, seconds, how many pieces of a second have you endured the force hitting you? And that's all that's going to matter. How much paint came out of the sprayer and hit you? And that's always going to be the sprayer's constant. And so it's just about how long am I in front of the sprayer. The longer I'm in front of the sprayer, the more paint I collect. It's that simple, and they're teaching it this convoluted nonsense. It's just, it's mind molestation. They're just molesting the young minds with this rubbish.
In order to give something some change in potential energy, you're going to have to raise it up away from the Earth's surface, and you're going to have a change in height.
So you're just going to have a change in the time you're going to allow it to collect energy. The height is just an amount of time you're going to allow it to collect gravitational energy. It's just changing how long you're going to be in the stream. How long will you be in the paint spray? Oh, fuck.
Or it's going to be the height above a reference surface. Okay? Now, the
Nonsense.
main thing that changes something's gravitational potential energy is when its height changes. Of course, you could change the mass, but usually we have an object. In order to change its potential energy, we raise it up into the air.
Right, no, again, you're just changing how much time will it be allowed to collect gravitational force before you drain it with a conductor, with contact.
So, for example, if we have a rocket and it's at the surface of the Earth, if we want to increase its potential energy.
All right, so it's just kind of silly to talk about something you're using a force to acquire potential energy. You're using energy to acquire potential energy. I mean, that's just kind of a ridiculous circumstance. So, they're talking about getting to some point where you're going to allow it to be, it overcame gravity, and now gravity is going to give back exactly what you overcame. So it's just a ridiculous way of doing the example.
Give it more potential
Of the potential energy
relative to the surface of the Earth, then we just raise the rocket up. We lift the rocket up. And it goes the same way with any object. You have something on the table, you have something on the floor, you want to give it more potential energy, then you just lift it up to a higher position.
So you just lift it up. So obviously the just lifting it up is an argument to be made, because if I take 10 years to lift it up, I'm going to overcome an awful lot of gravity. That's going to be a lot of seconds. All right, so that's going to be a lot of force I have to overcome. And if I lift it up very, very quickly, well, then I got to cross the stream really quickly, and it pushed very little on me. So obviously you did very little work to acquire your potential energy position. You did less work. The trick is you can't go fast and then just stop. You can't go 100 miles an hour and then just stop. You have to go 99, 98, 97, 96. So that's the trick. You can't just, you can't go a very fast speed to a very short distance.
All right, that's gravitational potential energy. Now we have the other form of mechanical energy we're going to talk about.
All right, so there's no form of it. So it has no form. So momentum you could understand because it's this mv quantity thing, okay? And you're just saying the velocity in a mass. So I can go, if I can have a big M, big mass, small velocity, and I can make it into a bunch of little masses with a V. And it's always going to add up to the same amount of total mv. I'm conserving this quantity. And now they introduce this silly notion that there's some other magical sparkly thing going on, some hobgoblin energy, that's somehow related to your velocity. And so the more velocity you have, the more of this sparkly energy you have.
That's kinetic energy. Kinetic energy is the energy of motion.
So we know momentum is the energy of motion also. So it's just, what's the point of saying the energy of the energy? Kinetic energy is the energy. Yeah, okay. So momentum can't be the energy though, because it's not, energy isn't equal to energy. It's just such a cheat, that they've stolen the word energy to only mean kinetic energy, and yet they'll use it as if they're talking about motion. So motion is energy, but it's only kinetic energy. It's not momentum energy.
In order to have kinetic energy, you need to be moving. You have to have some speed or velocity.
You have to have momentum. Yeah, you have to have an M and a V. And the silly thing is that somehow you're going to break something that always works. So momentum was conserved. Descartes certainly believed it was. I think Galileo believed it was, and I think Newton believed it was, substantially. I mean, Newton did say something about every now and then God needs to push the universe somewhere because there's a deficit something. But anyway, the idea is this conservation thing with momentum. So why would you need this kinetic energy thing? What do you need it for? What's its value? Because there's no example where you can use it. So he showed a rocket. Well, the rocket exhaust in kinetic energy doesn't equal what the rocket gets. The rocket gets the momentum of the exhaust. That's the equal and opposite reaction. So where does the kinetic energy play a role? Oh, that's right, it doesn't play any role at all. It's irrational nonsense, frankly. The rocket proves it. Because you just change how much energy your fuel has based on what you're pushing. You push something light, you have this much fuel. You push something heavy, you have 10 times the amount of energy in your fuel somehow. Magically, you're getting so much more energy out of your fuel when you push light things, but you get the higher velocity. And you push heavy things, your fuel is weak and you barely got any octane because, it didn't get shit out of it because you pushed something heavy. I mean, that's how stupid it is.
Okay, any object that is in motion has kinetic energy. All right, potential energy has to do mostly with your height. Kinetic energy has to do with your motion.
Oh, I mean, just ridiculous. I mean, obviously your height creates your velocity. Okay, and your kinetic energy is made out of your momentum. So, I mean, its momentum is right in the kinetic energy formula, so why pretend it's something other than just some bizarre, strange add-on to momentum? So momentum works perfectly rationally. everywhere. You don't need to fix it. And yet they fixed it by putting a half in front of the m and a square on the velocity, and it didn't fix anything. It doesn't make the universe more rational or more understandable. It didn't do a damn thing that's of any value. It's just such a tragic, stupid mistake that physics adopted something unproven and useless. Alright, the fact that you can... okay, we didn't get any new chat. Okay. What are we, still at 3 people or something? What's this? Let's see how many people are here. I tried to write it with 5. Yeah, not great. But nothing I can do about it.
The equation symbol that we will use is Ke for kinetic energy. And once again, since we're talking about energy, the unit is still the joule. James Prescott Joule, abbreviated with a capital J. And again, you can write down that something has a kinetic energy, for example, of 12,750 joules, like that. Okay? Now, when we calculate kinetic energy, this is the equation we're going to use. The kinetic energy is 1/2 mv squared.
Yes, for no rational reason. So again, momentum wasn't broken. There wasn't some circumstance that left everybody wondering, oh, it doesn't add up. Nothing makes any sense. It doesn't look like energy is conserved, so we need to fix it. That just isn't in the history. There wasn't anything broken that needed this silly formula to show up to fix it. This was just the delusion of a religious kook.
All right, the kinetic energy, Ke, is obviously the kinetic energy measured in joules. 1/2 is simply 1/2. M is the mass, it needs to be in kilograms. And V is the velocity in meters per second squared. Now, it is a V, and I did write down here velocity, but a lot of times we say speed. Okay, we use kind of speed and velocity interchange.
Yeah, so whatever. And speed is somehow a scalar, and so it's 60 miles per hour of speed and 60 miles per hour of velocity, and it's the same damn thing, and there's no ever distinction, and the speed is never different than the velocity, and yet they're going to pretend there's some kind of special kinetic energy speed thing that stuff has because of that stupid squared velocity.
Interchangeably, but you'll see something is moving with such a velocity, or something is moving with some speed of 10 meters per second. Then you have to put that into the equation, and you have to remember you have to square the velocity. It's only the velocity that's squared. 1/2 mv squared, like that. Okay? And again, it has...
Okay, yeah, just believe it because we say so, and it won't make any sense, and it means that it takes 25 times the fuel to go 5 times as fast. So don't pedal too fast on your bicycle because you'll get all worn out. And make sure you tell your parents not to step on the gas pedal because, boy, it really costs you a lot of money. Your college fund is just disappearing.
To do with your changes in motion or your speed. All right, now, for example, here we have a car.
Yeah, that won't obey any of this kinetic energy crap. So when I crash it, it won't crush 4 times the amount when I crush it with twice the velocity. So twice the velocity, I square the velocity, I won't get 4 times the energy out of the car. It won't do 4 times the work. It won't push 4 times as much stuff. It won't push 4 times the snow. It won't do any of these things. It'll never show up to do anything. It's meaningless mush, and it especially won't show up in the gas tank. So let me use the dickhead. It won't show up in the gas tank over here, okay, in the sense that you won't have to use 25 times the fuel to go 5 times as fast. The wheels won't take 25 times the energy to spin 5 times as fast. None of that crap will ever happen. All right, the physics is complete nonsense, and yet he's brainwashing kids with this crap. And he has to admit he's doing this video for kids. That's just evil, friend. You're talking shit to kids. That's just not a nice thing to do.
The car is standing still, it's not moving. Okay, it does have some mass, but because it's not moving, excuse me, it has no kinetic energy. In order to give it kinetic energy, it has to move like that. And as
Yes, and then it has some special capacity to do lots and lots of stuff based on this v squared nonsense, this quadratic increase in its capacity to do. And it's a delusion. A delusion, because it never does. There's no do, there's just delusion.
it moves across the page like that, then it's going to have kinetic energy. All right, you got to be moving.
Says you, no evidence. There really is no evidence that it's going to have kinetic energy. 3 times the velocity, 9 times the capacity to work, 4 times the velocity, 16 times the capacity. No, it's not going to happen.
Energy. All right, now the next thing, we did energy. Now we're going to do work. All right. Now we're going to do work, and work is done when a force is applied through a distance.
All right, so that's the big silliness again. The distance of the stream doesn't matter. The time you're going to be in the stream is all that matters. Distance is irrelevant. Time is everything. Blah, 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 blah. I mean, it really is that simple. This is just the only thing that's going to matter is how long are you in the paint spray. That's it. Doesn't matter what you do in the paint spray. It's just about, it doesn't matter distance, doesn't matter velocity, just matters how long were you in the paint spray. That'll decide how much paint you collected. That's how it all works. That's how the universe works.
Okay, you could write this down as a definition. It's kind of hard to come up with a definition for work. But work is done when a force is applied through a distance.
Okay, let's understand. So kinetic energy doesn't do work on the rocket. So the kinetic energy of the exhaust could be 2 million joules. The rocket will only get the 200 newtons of momentum. The momentum is the only thing that's going to move the rocket. So a ballistic pendulum, you shoot something into the big giant thing, it absorbs the motion. The only motion it will absorb is the momentum of the object. The kinetic energy, there could be 1,000 times more energy in terms of a number of joules. Nothing. You won't get any of it into the motion of the bigger object. I mean, these are just obvious tests. Kinetic energy fails dismally to do anything called work.
A push or a pull is applied.
All right, so we know there's no pull. So again, why are you teaching kids that there's pulls somewhere? There's no elemental pull. I'm an electron. I can't go wooey wooey woo. No, it's not going to work. But I can throw rocks at something and push it. Okay, that I can do. So you can throw a rock and push on something. But there's nothing else you can't do. You can't pull a rock. You can't pull on the object. All you can do is spit at it, like a sun spitting photons. You can spit at something, but you can't unspit. So there are no pulls. There's just an absence of push.
To an object, and the object moves. As you'll see, in order to actually do work, you have to apply a force. And when you apply a force to the object has to be moving.
So again, you can apply a force and it doesn't move. Lots of examples where you're just creating a pressure and it's got to all be converted into heat because it won't move. So I take 2 big steel balls on a Newton's cradle and let them crash into each other, and they'll bounce off of each other and barely create any heat at all at contact. Put a piece of paper between them and they'll hit and the paper will be a little smushed, but that's it. But I let them crash and I force them to stay together. They'll burn the paper. They'll start a fire. It's just a fact. So if something doesn't move, then you're converting the motion into some other motion. And the most logical motion to talk about is the motion of the atoms and their vibration, and that's heat. So if you have 2 things moving, they hit each other and nothing's moving afterwards, then you've probably created a lot of infrared radiation and other such evidences of heat.
The equation symbol for work is W, and the unit is the joule. Now there's this thing, the work energy principle, and when we talk about work and energy, we can interchange work and energy, which we'll talk about later in another video. But it also
yeah, you can interchange something that's never actually convertible. You can never convert the KE into this work thing. It never happens. It never does work.
has the same unit as energy, which is the joule, which is abbreviated with a capital J. And you could write down work. You did 75 joules of work, like that. Okay? So that's energy work. And when we calculate work, this is the equation that we're going to do. The work is the force.
So again, we're talking about distance when it's obviously about the force times time. How long are you being pushed by the force? How much is the, that's it. How long are you in the paint sprayer? How long are you in the stream? How long are you in the wind? All of these things will be decided because they're all time dependent. They're all moving a velocity that has a second in it. So they're all time dependent forces.
Force times the distance. Now sometimes with this equation, you'll see it'll say cosine theta over here.
So again, the distance won't matter. If you have a pre-existing velocity, then the force won't equal blah, blah, blah. So, I mean, all of this is just really bad physics.
In the basic class, the force and the distance are going to be in the same direction, so we're going to leave off the cosine of theta. So this is just the work is equal to the force that's applied times the distance the object moves. Once again, work is measured in joules. That's what W stands for. The force is the force, or excuse me, F is the force measured in.
So the joke is, right, is that in space, you hit something with a force and it moves a velocity. Twice the velocity is only going to be twice the distance. So there's not going to be any evidence in the overt distance that indicates the kinetic energy formula is realized, because there's not going to be anything that indicates you got 4 times anything, because you only got 2 units of distance. So it doesn't work. Yeah, it only works if you understand that the work, okay, is actually a conversion of one momentum into another.
Newtons. And then, of course, d is the distance, which is measured in meters. If you are given the distance in kilometers or you're given the distance in centimeters, you need to convert first into meters. All right? Now, here we have Doris, the lunch lady. She's going to go shopping. She's got her ladle there. She's going to go shopping with her shopping cart. And in order to get into the store, she has to apply a force. Now, if she applies a force and the shopping cart doesn't move, then she's not doing any work on the shopping cart, because
so again, that's the nonsense. Just like you hold your briefcase up in the gravity and somehow you're not doing any work because it's not going up. Yeah, well, no, it doesn't have to go up for you to be doing work. The stalemate means there has to be something getting hot. So you are doing work somewhere. You're heating something.
She applies a force, but the distance is 0, and the force times 0 is just 0. Like that. In order for her to be doing work, she has.
So the force can never be 0. It's just silly. Again, doesn't make any sense. I put a rock in the stream and the rock doesn't move. Well, then the stream gets hot. Fact. That's a joule tank experiment, essentially.
Has to apply a force and the cart has to move. So when she pushes the cart across like that, then she's doing work. But once she stops.
So it's all just transfers, and you can either transfer the energy or you can convert the energy. So you can transfer it into linear motion, or you can transfer it into crushing atoms. Okay, so there's different things you can transfer. There's different ways you can transfer the energy, but that's all you can do.
Even if she's still applying the force, she's not doing any work. Okay?
Silly.
So that's work and energy. And now we have power. All right, this is the last one.
So useless concept altogether. There's really just momentum. There's just a force over time. That's all there is. Power is not a real concept.
What is power? Now, I mean, a lot of people use power in different ways, but for physics, power is the rate at which work is done. That's the definition.
Yeah, who cares? All you care about is how much you got, how much juice is in the battery. You just want to know the watts, you know. The power it doesn't mean anything.
Although you can maybe write this one down. Instead, it's how fast work is done. The faster you do work, the more power you have, or the higher the power output is.
Yeah, so again, just doesn't really mean anything. Obviously, if you have a high voltage and a high amperage, you have a high wattage, well, the high wattage speaks for itself. You don't need to call it high power, but you already have high wattage.
Okay, so the equation symbol is a P. So when you put it into the equation, you have to use a P. And the unit is a watt, like W-A-T-T. The abbreviation for that is a capital W.
So the watt is just a joule, and so it's not just about power, it's about capacity. Watts tell you how much capacity just as well as they tell you anything else, so it doesn't mean anything, really. It's just a quantity. Now,
Most people have heard of watts, as we'll talk about in just a moment when we talk about light bulbs, because you have a 40-watt light bulb, or maybe you have an appliance at home and it's a 1,000-watt appliance, like maybe a hair dryer or something like that. So that's what the unit is, it's watts. And power, you could write down as the power, for example, is 450 watts. That's how much power you would exert, or that's the power output. Okay? So that's power. Now when we calculate power, we use this equation. Power is equal to the work divided by the time.
So again, it's just a poor use, because the time is, like I said, power is an absolute, you could argue, and measuring it in units of time isn't very useful. I mean, it's a total amount. It's like it's like measuring. It's like calling your mass something divided by blah 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 blah. Just complicate something that's simple.
All right, because we do work over time, and that's how fast we do work. All right, if we do so many joules of work in 10 seconds, we just divide the amount of work divided by the time, and you get the power output. P is the power measured in watts. W is the work measured in joules again. Work is measured in joules. And T is the time. And you have to remember.
So joules and watts are the same thing. So again, there's really no point in putting them with time, because these are two things that are the same thing.
That the time has to be converted, or has to be in seconds.
Just makes so much more sense just to replace one of those words and say, no, let's just call everything units of watts, or call everything units of joules. But let's just pick one of them and use that one.
Sometimes you get it in minutes or days or something like that.
I mean, you could even argue that temperature, in some respects, all these things should be in one unit.
At a time, you got to convert that into seconds. Okay, so there you go. That was a quick overview for those 5 important topics. I tried to go step by step. Start at the bottom and work your way up.
For what, 11-year-olds? Okay. You ought to just say somewhere in the video here, somewhere, this is for 11-year-olds. Yeah.
And you start with mass, and then weight, and then energy, potential, and kinetic, and then work.
Yeah, but it's all wrong, so it should be for dead people. Yeah. Miscarriages. This is physics for miscarriages. Yeah, yeah. Aborted fetuses. This is physics for them.
And then power. Thank you so much for watching. Hope you found the video helpful. If you did, please do all of the following 5 things. Subscribe to my channel, Step by Step Science. Please support my YouTube.
Oh, please do all that stuff for me too. Don't leave me out.
YouTube channel. You should click on the notifications so you don't
Please don't hate me. Please, please, please. Don't drive me off the internet by neglecting me terribly. Ooh.
miss anything. The notifications bell. You should give us a thumbs up. You should leave us a nice positive comment.
You shouldn't post crap on top of your video. But whatever.
Please don't forget to share this video. Thank you so much for watching.
Fun with natural frequencies. Whatever that even means. Yeah, like, oh wow. Those scary unnatural frequencies.
See you in the next video.
Alright, the end. Oh, it's good you told me that. I sometimes neglect to be able to figure out that it's the end. It's good for somebody to tell me it's the end, because I wouldn't have figured that one out all my own. Oh, God, it does exhaust one. Planet Earth. We're all still here. We're 5 people. Yeah, it is just terrible. Nothing I can do about it, though. So, what am I looking for? I'm looking for... Yeah, there's 6 now, so haha, I'm up to 6. So I believe I'm out of coffee. Yep. So I think my time here will be short. So we'll sum up. Summing up, everybody's a stupid fuck. And I have to sit there and interact. At least I don't have to smell you. You know, I don't have to listen to any of you. You know, you're not talking, so that's good. Let's see, what else can I say? And I guess I don't mean you, the ones watching now, the 6 people. You know, I mean obviously the 100 other morons that'll show up later to talk crap and somehow, you know, pretend that they can hurt my feelings, and just talk trash, like, you know, the arrogant pieces of scum that they are. And, you know, that's just sort of the truth, that, you know, people who talk shit about other people lie about them. You know, they really should get what they deserve, you know, and it's all trying to figure out how you do that, you know, in a civilization. Now, I used to pillory people, which seems a reasonable thing to do, frankly. You know, just to say, you know, to people who are thieves and liars and crooks, you know, that you've insulted all of our dignities with your cheating, you know, and so we're going to insult your dignity. You know, and throw dog dew on you and shit. You know, and, you know, it seems appropriate, but to me it just doesn't last long enough. You know, you pillory them for a few hours or something. You know, you really should do it for a few 100 years. You should just keep pillorying them long after they're dead. You know, you should every now and then be able to just go over to their, you know, maggot-infested skeleton and give it a kick in the face. But whatever, that's just me. Yeah, I think it would be very nice to take the people who just, they can't learn a lesson. You know, they live a life and they don't recognize what humility is and how, you know, they really can't, they can't talk beyond their capacity to defend what they're saying. And, you know, and that it is just, like this video, like I say, he's a nice enough guy, makes his little physics videos, but the fact is, it's just wrong, and it's a molestation. It's a lie about what Newton said. It's a lie about what they have evidence to demonstrate, and so it's just lying to kids. And obviously he's not doing that on purpose, but I think he could know, you know, if he was fair and reasonable, that he really has no business talking this shit, because he really can't back it up with anything. You know, it's like the dickhead, you know, implying that I'm a drug user. Not in my youth, yeah, sure. But yeah, I don't drink to excess. I mean, I might go through a bottle of booze in a year, you know, something like that. So yeah, I don't use drugs. So why bother with some crap like that? Why lie about somebody else? I mean, what's the point of that shit? It's just your character that you're just demonstrating you don't have any character. You know, you're just a liar. You can't make an honest argument, so you make dishonest ones. It's just really scummy. Alright, so I guess that's all the video you're going to get. Yeah, for today. And let's see if this is any advice on how to lose weight. Yeah, don't eat as much. So he calls himself fat person. So I think you're just another dishonest, lying sack of trolling shit. And it's just disappointing that even those kind of subjects people abuse. You know, it's a serious problem, frankly, in this country, you know, this whole eating thing and weight. And it's just an addiction, right? And the simple truth is you can eat the same amount you're eating now if you just lose the weight and just maintain it. You know, it just has to be a little bit less to maintain a lower weight. It's just about maintenance. The storage isn't really doing anything. It's just making you fat. So just get rid of what you stored. And yes, it's a little bit inconvenient for a month. Okay, deal with that. You know, but the system's pretty simple. You know, if you have to eat too much, then you're going to have to poo too much. Okay, that's the secret. It's all about metabolism. I eat almost nothing, you know, and it sits inside of me for a while because my body has to get everything it can out of it. But, you know, so if you eat a lot, you got to poo a lot. It's the simple answer. And, you know, that's the you got to get things to move through you quickly. So eat a bunch of lumpy, like, eat peanuts and don't chew them very well. You know, eat things that are hostile to your system, and then your system will get rid of it quickly. So, I mean, fat is sort of like that. Fat has a lot of calories, but your body looks at fat cells and it kind of just says, I don't want to have anything to do with that shit, and it shits it. So, you know, you could have the high fat diet, and maybe you can lose some weight that way. Your body really doesn't want to work hard, so it likes sugar, and it likes bread. You know, it likes simple things that it can pull all the resources out of. So if you want to lose weight, don't eat bread, and don't consume sugar too much, because frankly your body gets all of it. You have to try to figure out how to eat stuff that you can't absorb. You know, but anyway. But it's, you know, addiction sucks. But I'm just saying it's really not the same. You know, it's not a hard addiction, you know, this idea of playing with how you eat. You know, and just the idea of just making a rule that, you know, you won't eat a certain food on a certain day. That kind of, you know, you just do little incremental confinements, and it becomes natural pretty quickly. I haven't eaten a breakfast in 30 years. I haven't eaten a lunch in 45 years. You know, it's not a huge sacrifice. Oh, I have to have a lunch. No, you don't. So anyway, thanks for the advice. Just realized I was all about my mindset. Yes, so everything's a head game, frankly. Everything, you know, that happens in here, you know, that's going on that you think is interesting. It's all in the brain, okay? And it's just about getting your brain to do things that are good for you versus things that are really bad for you. And those are just called habits. And, you know, it's always, like I said, I've been addicted to nicotine almost my whole life. And I don't have the brain withal to say, fuck that. I mean, even if it sucks for 2 weeks, just let it go. Separate yourself from this annoying habit. But my brain yells at me, no. It's as if the brain will crumble and die, you know, without nicotine. So it is funny, you know. So do as I say, not as I do. Okay, I'm just saying. Yeah, well, it's actually about your metabolism. There's a word called metabolism, and you have to get your metabolism to be symbiotic with your consumption. So if you're consuming a lot, you need a metabolism that says, I want to shit a lot. And if you're consuming very little, then you want a metabolism that holds on to it. But any imbalances, no point in eating a small amount if your metabolism is saying, keep it forever, but you're still in trouble. It just doesn't take. We are amazing machines. I mean, it's just amazing what you can get away with and survive. You really can live on bread and water. I mean, it's perfectly doable. Like for years. Because I'm almost eating nothing. I mean, it's rice and a few vegetables. And yeah, I'm not. I'm not. I don't feel great, and I'm not doing great. But the fact is, I'm alive, so it does work. So anyway, all the awesome people are here. Oh, it's just a room full of awesomeness. Yeah, probably not. But anyway, but it is. It's just one of these things that bugs me, just because there's so many fat people having kids. I mean, my own family relation, cousins, whatever thingies, these people that I know from they're all fucking fat. I mean, fat. They're not just plump. They're not just plumpies, but they're fatties. And they're pooping out kids, and you're just like, you can't even control your own fucking eating habits, and you're going to control somebody else's maturation in life? I mean, it's just... There's people on this street that, they fostered a retarded kid, just for the money, no doubt. And, the kid's way overweight, and you're saying, how are they allowed to have the kid if they can't get it to control its weight? It's a fucking disaster just waiting to happen. I mean, 10-year-olds should not be 100 pounds overweight, and people who have a 10-year-old who's 100 pounds overweight shouldn't be still having a kid that's 100 pounds overweight. It just shouldn't happen. It shouldn't be allowed. There should be a law against it, for fuck's sake. So anyway, it's just yeah. But it's really annoying. I mean, people that are just so obnoxious and arrogant. I mean, they can't control their own eating habits. They can't keep their physical body in decent condition. And they have fucking kids. What the fuck are they thinking? I mean, what kind of role model is that? And then you're just saying, I don't care whether I drop dead and abandon my child. I mean, it's so wrong in so many ways. It's just fucking evil. Alright, anyway. So, till the next time and such and so forth and whatnot. So the dickhead, he made some comment about my videos being an hour and a half long or 2 hours long. Yeah, well, obviously these are videos intended to be, for the audience, blah, 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 blah. They're not exactly the hard physics videos, blah, blah, blah. And so why not? And I made all those videos that are 10 minutes long, and they won't reply to those. They're these obnoxiously silly complaints. They're just so irritating. And that's all they have, though, is obnoxiously silly complaints. They can't make any physics arguments. I just didn't think this would be the hard part. Getting people to argue the argument. I thought that would be the easy part. Making the arguments, that's the hard part. Having an argument, that should be the easy fucking part. An argument that's on the subject. And they just can't stay on the fucking subject. 25 times the fuel to go 5 times as fast. Yeah, they can't get anywhere near that subject. Ooh, crash. Yeah, so my tab crashed. So how do I end my stream? I'm stuck here forever? Oh, fuck. What am I going to do? I'm stuck here forever. Because the tab crashed. I can't hit the button. There's no tab. Alright, it's resetting, I think. Yeah, so, okay. So, now I have my end button, so I'll do that. So anyway, so till the next time and such, appreciate the few people that do show up. It's something, I guess, but yes, these rooms they need more participation from, more feedback, more, interaction, something challenging, something, it needs all of that kind of excitement to be really interesting. So we have to, we have to get, somebody has to make an interesting video. That would be really cool if somebody actually made an interesting video. But anyway, till the next time and such and so forth and whatnot. I can only do my part. Of course, I continue to do my part. And the world doesn't do its part. Sadly.